Hello there, Chem 2922ers. Welcome to the molecular spectroscopy section of the course. I've got a few topics that we're going to work through, as you can see here. This short video is covering the first topic, Introduction to Fluorescence. What fluorescence is, a little bit of the theory behind it, what makes a molecule fluorescent, and a few other things like that. Here are some learning objectives for this first topic. I'm not going to read through them right now for you, but it's probably worth coming back to them once you've been through the video and just have a look at them and see what you've learned under each of these topics. Okay, well, here's a good place to start. What is fluorescence? You've probably all got some idea of what it is. You'll have at least heard of it, might have seen it. Quite simply, it's emission of light by a molecule. Many molecules can absorb light, or if you prefer, electromagnetic radiation, of UV and visible wavelengths, and what happens is electron density redistributes. An electron is promoted to an orbital of higher energy and generates what we call an excited electronic state. So, absorption of light, promotion of electron to orbital higher energy, get an electronic excited state. Now these are unstable and will decay usually pretty quickly back down to the ground state, and that decay is typically sort of nanoseconds on the time frame of 10 to the minus 7 to 10 to the minus 9 seconds. And when that decay occurs by emission of light, so just as absorption of a photon can generate the excited state, emission of a photon can relax the excited state back to the ground state. And when that occurs, that's fluorescence. So that's what we call fluorescence, is this radiative relaxation of an electronic excited state. There's some closely related phenomena that we're going to discuss, which you may have also seen or at least heard of. Chemi and bioluminescence and phosphorescence. One of the great things about working in fluorescence is there is no shortage of pretty pictures. So here's a little selection for you. What we've got in the top left is just conventional fluorescence. So we've got a couple of cuvettes, and in those cuvettes is a solution containing the molecules indicated. Probably concentration is around a few micromolar, so there's not much material in there. And the solvent's probably something like ethanol or chloroform. And the cuvettes are just sitting there under a UV lamp, so you can see that the molecules are absorbing the UV light and then fluorescing nice red on the left and yellow on the right. Bottom right corner is phosphorescence. So someone's there holding a crystal. It's actually a calcite crystal. We'll look at this one again later on. And there's been a flash of light. So this is a series of photographs taken after a flash of light. And so the crystal absorbs photons from that flash of light, and then over a long period of time, so many seconds, somebody's just sitting there holding that crystal is emitting light. And that's one of the key differences actually between fluorescence and phosphorescence. So if in the top left, the person taking that picture turned off the UV lamp, the fluorescence would stop pretty much instantaneously. Whereas with the phosphorescence, there's the lamp flash, and then for quite a few minutes after that lamp flash, there is phosphorescence. But that phosphorescence gradually decays away over time. The other two, chemiluminescence and bioluminescence, are different in that they are caused not by absorption of light, but by a chemical reaction. So the glow sticks in the bottom left, you're probably quite familiar with. So there are some chemicals inside the glow stick, and when you crack them open, a reaction starts, and that reaction actually leads to molecules getting into an excited electronic state, and they then relax by emission of light. And the bioluminescence example is some little bacteria. So that's actually an agar plate up there in the top right. And some bacteria have been cultured on that plate, and they are actually generating light as they go about their sort of required metabolic processes. So they've actually got an enzyme in them called luciferase, which, when it does what it does, actually leads to emission of light. So that's bioluminescence. Okay, let's meet this energy diagram here. Very handy, very convenient way of showing what's happening in a molecule when photons are absorbed and emitted. So the y-axis is energy, just increasing energy, and the x-axis is not so important. We don't have to worry about that. It's just call it molecular coordinate. And what we've got is horizontal lines to show allowed states. So these are the allowed electronic states that the molecule can have, and they're labelled S0, S1, S2, and so on up to Sn. S0 is the ground state. So where's that? Here we go. Ground state, S0. And the S means singlet. It means it's got singlet spin, which means that if there's electrons in there, then they have to be spin paired. The S1, S2, Sn are excited electronic states. And transitions between these electronic states are indicated by the vertical arrows. So when we go up in energy, we've got a photon being absorbed, and when we go down in energy, we've got a photon being emitted. Absorption can go from any state as long as the spin is conserved. As long as we go from a singlet state to a higher singlet state, such as any of these blue arrows is indicating, then that's okay, that's spin allowed. Then emission also can go from a higher state of the same spin down to a lower state. So if we're going to end up in a singlet ground state, the photon has to be emitted from a higher singlet state. So this is just a nice diagram and convenient way to show these processes. Okay, now there's more going on than just absorption and emission of photons. There are what we call non-radiative processes involved as well. And we can show these on these energy diagrams too. Now what we've got here are the vibrational energy levels. So that's now these little lines here. So the thick black lines are the electronic energy levels, and within each electronic level there are a series of smaller vibrational energy levels, and we're going to talk a lot about vibrational energy levels later on when we talk about infrared spectroscopy. Now, excitation, absorption of a photon can go into a higher vibrational level of an excited state. So you can see here where it's drawn. These transitions are ending up in higher vibrational levels within S1. And emission can drop down into any of these vibrational levels. So you don't have to drop into the bottom vibrational level of that electronic state. You can go into a higher vibrational level within that ground electronic state. Now, interestingly, emission almost always occurs from here, from the lowest vibrational state of the lowest excited singlet state. And this is a really important observation and actually has the name Cash's rule. So, where does this Cash's rule come from? Well, first of all, there's our absorption of a photon, and we've gone up into a higher vibrational level of S2. And then what happens soon after is the system drops non-radiatively. So there's no photon being emitted here. This is non-radiative by a process called vibrational relaxation. And that's this. The system gets rid of vibrational quanta of energy. So these are much smaller quanta of energy. it relaxes by getting rid of these vibrational quanta, and the system then gets down to the bottom of that electronic state here. So this is the lowest vibrational level of S2. Now, another process can occur called internal conversion, where the system converts from, if you like, V0 of S2 into some higher Vn of S1. And then following that, there's more vibrational relaxation down to the bottom of S1. So these two phenomena, vibrational relaxation and internal conversion, occur to get the system down to the bottom of S1. Now, the energy gap here is much bigger between S1 and S0, so internal conversion and vibrational relaxation are not as efficient, and this means that fluorescence can occur. So let's have a look at these approximate timescales. Absorption is effectively instantaneous. This is 10 to the 15 per second is the rate constant. That's a femtosecond. So the molecule adjusts its electron distribution in a femtosecond to take on board that photon of energy. Vibrational relaxation are both very fast. The rate constants here are up around 10 to the 11 per second. This, if you like, occurs in picoseconds. Now, fluorescence, by comparison, is slow. It takes nanoseconds, which is still ridiculously fast. The rate constants are around 10 to the 7 to 10 to the 9 per second. The phenomenon of fluorescence takes maybe 10, 100 nanoseconds, something like that. So what this means is, because vibrational relaxation and internal conversion are orders of magnitude faster, once the system has absorbed the energy and got into the excited state up here, these processes occur very quickly, and the system relaxes down to the bottom of S1, and then the fluorescence occurs. That is the origin of Cash's rule. Now, there are some consequences of Cash's rule. The first one is that because of the loss of energy to vibrational relaxation and internal conversion, fluorescence is always at a longer wavelength, a lower energy than absorption. The energy of the photon is actually given by the size of the arrow in these transitions. And so you can see these arrows, the fluorescence arrows, are smaller than the absorption arrows. And this difference in energy is called the Stokes shift. Another consequence of Cash's rule is at room temperature, spectra are broad because you can have these loss and gain of vibrational quanta as well as rotational quanta. So you don't get thin spectral lines, you get broad spectral bands. And you can sometimes see these vibrational bands. So the full emission spectrum will contain photons from this transition, from this transition, and from this transition. And you can see these all have different amounts of vibrational energy involved in them. And because of the size of these vibrational levels, here and here are quite similar, absorption and emission spectra are often a mirror image. And here's a nice example of some mirror image spectra. So this is a molecule that was made by Sue Maniam. Some of you may have met Sue along the way. And she's a synthetic chemist and likes to make fluorescent compounds. And here's one that she made. And this is the absorption over here. And this is the emission here. And you can see there's sort of a mirror image in the absorption bands here are mirrored over there in the emission. Now we'll talk about these spectra a bit more in the lecture. Okay, here's a little change of tack. How do you measure that emission spectrum that we saw on the previous slide? Well, you've all probably used the Carey Eclipse fluorimeter made by Agilent up in the second year lab. If you've done either Prac 4 or Prac 9, I think it is, you'll have used the fluorimeter. So here's what's inside, a little cutaway to show you what's in there. So we'll start at the back end. The detector is a photomultiplier tube, so that's simply a device which, when a photon of light hits it, it triggers a cascade of electrons which forms a signal, and so that's then how that photon is detected. So that photon is multiplied up to give lots of electrons and a detectable electronic signal. And that detector sits at 90 degrees to the excitation. So emission is at 90 degrees. Now, simple reason for that, which I'll let you work out for yourselves. Now, there are gratings on both excitation and emission side, and these are for wavelength selection. So you can see what's shown here is full spectral light, so that's white light, from a xenon lamp, that's the excitation. And the grating then selects which wavelength you want to excite the sample with. So in the picture here, blue has been selected. There's the sample in there, and the fluorescence is shown by the orange line. So they're keeping the right color arrangement there. Orange light is lower energy than blue light, so that's recognizing that there is a Stokes shift. And if you wanted to measure a different wavelength, then you can scan the monochromator with the grating in it on the emission side. And so that's how you get that whole spectrum, by scanning through those emission wavelengths. Now let's meet an excitation spectrum as well. So as I just mentioned, the emission spectrum is fixed excitation at one wavelength and then scan across different wavelengths to measure the fluorescence. And you get a spectrum that looks like this. That's the emission. You get fluorescence intensity emitted as a function of wavelength. If you turn the measurement around, you now fix the emission monochromator at a certain wavelength. Maybe you fix it here. Then what you do is you scan the excitation wavelength. So you just excite your sample with different wavelengths, scan through on the excitation side, and you just measure the intensity of fluorescence at this fixed detection wavelength and see how that intensity varies as you go through the different excitation wavelengths. And you get a spectrum that looks like that. And the excitation spectrum looks very similar to an absorption spectrum. Again, I'll leave you to think about why, and we'll discuss that in the lecture. Okay, now here's another phenomenon that we need to talk about. It's called intersystem crossing, and it's a competitive process which can deactivate an excited state. It's non-radiative, and what happens is an electron changes spin, and the system, the molecule, goes into what is called a triplet state. So the system, if you like, is the molecule, and it goes from being in a singlet arrangement to a triplet arrangement. So it's intersystem crossing from one spin state to another. So we've excited the molecule, we've absorbed a photon, gone from S0 to S1. There's a little bit of vibrational relaxation down to the bottom of S1. And while we were waiting for the system to fluoresce, intersystem crossing got in first. And it can be really quite competitive. Some molecules actually will do a lot more intersystem crossing than they will do fluorescence. So rate constants for intersystem crossing can be up to 10 to the 9 per second, which competes very readily with fluorescence. So when intersystem crossing occurs, the system goes into the triplet manifold. And again, vibrational relaxation occurs for the system then to get down to here, to the very bottom of the triplet state. So if we have a look at what's happening with electrons, they're there paired in the bottom of S0. When a photon is absorbed, it's promoted, gets to here, goes to the triplet state, and now what makes the triplet state different to the singlet state is that the spin over here can be either up or down. It doesn't matter. It's no longer aware, if you like, of the spin of the electron remaining down in S0. And the name triplet comes from the fact that there are now 3 arrangements that these electrons can have. They can both be up, they can both be down, or they could be paired. It doesn't actually matter. And just like in NMR, when you're looking at spins, the probability is 2 to 1 to 1. Okay, let's meet phosphorescence. This is also spontaneous emission of a photon from an excited state. The difference between phosphorescence and fluorescence is that phosphorescence is emission from an excited triplet state. So if you remember, we've just been talking about fluorescence. That's emission of a photon from an excited singlet state. So if you're going from an excited triplet to a ground singlet, the change of spin is not 0. This means it's a spin forbidden process and is therefore quite slow. So if we're going from T1 down to S0. This means that phosphorescence is usually pretty weak at room temperature. It's quite rare to get bright phosphorescence at room temperature, and that's because non-radiative relaxation, vibrational relaxation, is competitive with phosphorescence, and that's how the system relaxes. So if we have a look at the energy diagram here, here are our electrons in the ground state. Absorption of a photon goes up into excited singlet state. Vibrational relaxation quickly gets the system down to the bottom of S1. Now, if intersystem crossing is fast and is competitive with fluorescence, so that fluorescence doesn't occur, this electron goes over into the triplet state. And we indicate that we've got triplet spin by drawing the electrons both pointing the same way. And then what happens is we go from the triplet state back down to the ground state, and that's the phosphorescence. That's this bit here. Now, as I said, phosphorescence is pretty slow. When it does occur, it can occur over milliseconds or even many seconds or minutes kind of time scale. And so that brings us back to the little example we had at the start, this calcite crystal with its metal ion inclusions, showing this very fancy multicolored phosphorescence. So you measure phosphorescence just like you do fluorescence. You use a fluorimeter, you put the sample in, detection is at right angles with the photomultiplier tube, etc. Except what you do is, rather than continuously illuminate the sample, you actually just flash the sample with a bright burst of light and then measure the spectrum after that. Generally, to measure though, you have to cool the sample down. If you use a liquid nitrogen cryostat, you measure it down at 77 Kelvin. But metal complexes or crystalline materials which are very rigid, such as this calcite crystal, often show room temperature phosphorescence. Now, why is the phosphorescence in this sequence changing colour? There's an interesting question for you to think about. We'll discuss that in the lecture too. All right, finally, here is a very busy, all-encompassing energy diagram. And these diagrams were pioneered by a fellow called Alexander Jablonski, who was a great photophysicist in the early parts of last century. So these are known as Jablonski diagrams. And the features are transitions indicated by arrows and energy states indicated by horizontal lines. So you can see all the phenomena here: internal conversion, vibrational relaxation, absorption, emission, intersystem crossing, are all indicated with some indication too of their time scale. Now there's another one here mentioned called delayed fluorescence, which you don't have to worry too much about, but it is quite an interesting one. Now what happens here is if you get intersystem crossing to the triplet, but rather than phosphorescence or non-radiative relaxation back to the ground state, if the system actually does reverse intersystem crossing, that's this arrow here, so we'll call that ISC prime, reverse intersystem crossing, goes back to the singlet state and then emits fluorescence. That fluorescence has been delayed by that little visit to the triplet state. So that's what that one is. Okay, well, as I said, it might be worth going back and having a look at the learning objectives to see if they make sense now that you've listened to this video.